Why is the sim-to-real gap so hard to close in robotics? Imagine training a robot in a computer simulation, then sending it out into the real world and expecting it to perform perfectly. It sounds simple, but it's actually quite tricky. When robots learn in virtual environments, they often struggle to do the same tasks in real life. This is because the gap between simulation and reality is bigger than it looks. One big reason is how robots perceive their surroundings. Simulated sensors like cameras or lidars create data that is often cleaner and more predictable than what real sensors produce. Real sensors pick up noise, reflections, shadows, and lighting changes that simulations usually ignore. When a robot trained on perfect images tries to navigate a real room, it might get confused by these differences. Another challenge is how physics are modeled in simulations. Physics engines try to mimic how objects move and interact, but they are not perfect. Small errors in modeling friction, impacts, or how materials deform can lead to big differences in how a robot moves. For example, a robot arm might grip objects differently in real life because the simulation didn't accurately capture the grip's friction or the object's weight. Simulations also simplify many details to run faster. They might ignore tiny environmental variations or the exact mechanical properties of robot parts. This means the robot's learned behaviors might not work well when it encounters real-world quirks. For instance, a robot might slip or stumble because the simulation didn't include those tiny surface irregularities. Real environments are unpredictable and constantly changing. Lighting can vary, obstacles can move, and sensor noise can fluctuate. Simulations often cannot replicate this full range of variability. So a robot trained in a controlled simulation might not handle unexpected situations well in the real world. Training robots with data is another issue. Methods like reinforcement learning need a lot of data to learn good behaviors. Collecting this data in real life is expensive and risky. So, most training happens in simulation. But the policies learned there tend to overfit to the simulated conditions and don't adapt well outside of them. Actuator differences also add to the problem. Real motors respond with delays, backlash, or where that simulations don't account for. This means a robot's precise movements learned in simulation might be hard to reproduce in real life. To bridge this gap, researchers use techniques like domain randomization. They vary simulation parameters like lighting, textures, and physics during training to make the robot more adaptable. They also use domain adaptation, where they translate simulated images into more realistic ones using advanced algorithms. Improving simulation fidelity by making physics models more accurate also helps. Some teams combine imitation learning, where robots learn from human demonstrations, with reinforcement learning to make policies more robust. They also incorporate real-time sensor feedback and fine control of joints to adapt on the fly. Closing the sim-to-real gap is vital for many applications like robotic manipulation, autonomous navigation, and legged robots climbing stairs. For example, training a four-legged robot to walk in simulation saves time and reduces risk. But getting that skill to work reliably on a real robot requires overcoming many of these challenges. In the end, the main reason the sim-to-real gap is so hard to close is because simulations can never fully match the complexity and unpredictability of the real world. Improving this requires better simulation tools, smarter learning algorithms, and more adaptable control systems. Only then can robots truly transfer what they learn in virtual worlds to real environments seamlessly.